Deep in the vast ocean of space, hidden among the swirling galaxies and glittering stars, lurk monsters unlike anything in our solar system. Not black holes, not rogue planets, but something even more bizarre. Picture an object so dense that a single teaspoon of its material would weigh 1 billion tons on Earth. Now imagine that same object spinning faster than a kitchen blender, wrapped in a magnetic field so intense it could distort atoms from thousands of light years away. These are magnetars, cosmic powerhouses that defy logic and stretch the very fabric of reality as we know it. What makes these alien neutron stars so extraordinary? Think of the strongest magnet you've ever encountered, maybe the one stuck to your fridge. Now multiply its strength by a quadrillion, and you're still nowhere close to the unimaginable forces at work around a magnetar. Their magnetic fields are so extreme that they twist the rules of physics into knots, creating environments where matter behaves in ways that would make even pause. These aren't just dead stars, they're natural laboratories, revealing secrets about the universe that we could never uncover on Earth. From that ripple across space-time to bursts of energy brighter than 1 million suns, magnetars are rewriting the cosmic rulebook right before our eyes. But why should we care about these distant, violent objects? Because buried in their explosive behavior are clues to some of the biggest mysteries in science. How does matter behave under conditions so extreme they seem impossible? What happens to space and time when subjected to forces beyond comprehension? And could these cosmic powerhouses hold the key to understanding the far future of our universe? Strap in, because we're about to take a journey to the edge of known physics, where the ordinary becomes extraordinary and the impossible becomes real. By the time we're done, you'll never look at the night sky the same way again. To grasp the sheer power of a magnetar, we have to go back to the violent moment of its birth. When a massive star, many times heavier than our sun, reaches the end of its life, it doesn't fade quietly. Instead, it detonates in a supernova explosion so powerful it can outshine entire galaxies for weeks. But in the chaos of that destruction, something extraordinary happens. At the core, where gravity crushes matter beyond recognition, a neutron star is born. And under just the right conditions, that newborn star becomes something far stranger, a magnetar. What sets these cosmic beasts apart? It all comes down to their unimaginable magnetic fields. While a typical neutron star already has a magnetic field trillions of times stronger than Earth's, a magnetar cranks that up to a whole new level. Picture the entire energy output of the sun, squeezed into a magnetic field smaller than a city. That's the kind of force we're dealing with, so intense it can literally bend the fabric of spacetime around it. And that's when things get truly bizarre. These magnetic fields don't just sit there. They writhe, twist, and snap like cosmic rubber bands under tension. When they shift suddenly, they trigger violent ruptures on the magnetar's surface that send shockwaves rippling through space. These quakes release energy in bursts so bright they can be detected halfway across the universe. Some of these flashes last just milliseconds, yet in that blink of an eye, they release more energy than our sun will emit in 100,000 years. But the real mystery is what happens inside these objects. Under the crushing weight of their own gravity and the mind-bending strength of their magnetic fields, the very atoms inside a magnetar are stretched and warped into shapes that shouldn't exist. Protons and neutrons are forced into bizarre arrangements, creating states of matter that can't be replicated in any lab on Earth. Some theories suggest that beneath their surfaces, matter might even crystallize into a sort of ultra-dense nuclear pasta, structures so strange they sound like science fiction. Yet for all their violence, magnetars might hold the key to understanding some of the universe's deepest secrets. Their extreme conditions act like a cosmic microscope, letting us study physics in ways that would otherwise be impossible. From the behavior of matter at incomprehensible densities to the very nature of magnetic fields themselves, every flicker and flare from these distant monsters teaches us something new. And as we unravel their mysteries, we're not just learning about magnetars, we're glimpsing the fundamental forces that shape everything in existence. The origins of a magnetar's monstrous magnetic field remain one of astrophysics' greatest puzzles. To understand how these cosmic powerhouses become so unimaginably strong, we need to peer into the chaotic moments following their birth. When a massive star collapses into a neutron star, its core undergoes transformations that would make even the wildest alchemist blush. Under pressures 100 trillion times greater than Earth's atmosphere and temperatures hotter than the sun, protons and electrons are crushed together into a sea of neutrons. But something extraordinary must happen to turn this already extreme object into a magnetic titan. One leading theory suggests the secret lies in quantum chaos. In the first seconds after collapse, the newborn neutron star's core might become a swirling ocean of exotic particles, hyperons, quark-gluon plasma, or other states of matter we've never observed directly. This quantum soup could generate colossal electric currents as particles spin and interact at nearly light speed, amplifying the magnetic field to mind-bending levels. Picture trillions of microscopic magnets all aligning perfectly, except in this case, nature's magnets are subatomic particles dancing to the tune of quantum physics we barely understand. But there's another compelling possibility, the dynamo effect on cosmic steroids. When a massive star collapses, conservation of angular momentum causes its rotation to skyrocket. Imagine an Olympic figure skater pulling in their arms during a spin, but instead of reaching a few hundred rotations per minute, the newborn neutron star might spin hundreds of times per second. This furious rotation, combined with the turbulent motion of superheated plasma in its outer layers, could act like a natural amplifier, twisting and strengthening magnetic field lines until they reach magnetar-level intensities. What makes this mystery so fascinating is that both theories could be right or completely wrong. Observations show that only about 1 in 10 neutron stars becomes a magnetar, suggesting there's some special ingredient in their formation that we haven't identified yet. Some researchers speculate it might depend on the exact mass of the original star, or the angle at which it collapses, or even the presence of magnetic fields in the star's initial composition. Every new magnetar we discover adds another piece to this cosmic jigsaw puzzle. The implications stretch far beyond magnetars themselves. If quantum effects in their cores really can generate such extreme fields, it could revolutionize our understanding of nuclear physics. Alternatively, if rapid rotation proves to be the key, we'd need to rethink how angular momentum behaves under conditions we can't possibly recreate on Earth. Each flicker of light from these distant monsters carries encrypted messages about the fundamental laws of the universe. We just need to learn how to decode them. Perhaps most remarkably, magnetars might be showing us glimpses of physics that don't exist anywhere else in the known universe. Their magnetic fields are so strong they approach a theoretical limit called the limit, the point where the vacuum of space itself becomes unstable. At this threshold, empty space should theoretically start producing particle-antiparticle pairs spontaneously, turning the area around a magnetar into a seething quantum foam. If we could observe this phenomenon, it would provide the first direct evidence that even nothingness, the vacuum we call empty space, has properties we're only beginning to comprehend. This is why magnetars aren't just cosmic oddities, they're nature's ultimate physics experiments. Every time one erupts in a burst of energy or unleashes, it's performing science we could never replicate in any laboratory. The answers hidden in their magnetic fields might one day explain everything from the nature of dark matter to the fate of the universe itself. For now, each new discovery raises as many questions as it answers, keeping astrophysicists awake at night, not just from the excitement, but from the humbling realization of how much we still have left to learn about the cosmos. If earthquakes seem terrifying, imagine living on a magnetar, where the ground beneath your feet isn't just rocky crust, but a crystalline shell of neutron-rich material harder than diamond. Now picture that shell cracking under the strain of a magnetic field so powerful it could rip electrons from atoms thousands of miles away. This is the reality of cosmic tremors that unleash energy on a scale dwarfing anything in our solar system. When a magnetar's crust fractures, it doesn't just shake, it detonates. The resulting gamma-ray flares can outshine every star in the Milky Way combined, yet last barely a tenth of a second. What causes these apocalyptic ruptures? Unlike Earth's tectonic plates grinding slowly over, a magnetar's crust is locked in a deadly tug-of-war between two titanic forces. On one side, gravity compresses the star's surface into an ultradense lattice. On the other, the magnetic field, threading through the crust like invisible wires, twists and pulls with enough force to warp spacetime itself. When the tension becomes unbearable, the crust snaps like an over-tightened guitar string. The energy released sends shockwaves racing through the star at half the speed of light, vibrating its entire structure like a gong struck by the gods. These aren't just spectacular light shows, they're for physicists. The vibrations from a carry secrets about the magnetar's interior, much like how seismographs reveal Earth's core. But here, where things get weird, the vibrations don't behave as expected. Some ripple outward in strange, spiraling patterns, suggesting the crust might be a bizarre hybrid of solid and superfluid states. Others vanish entirely, as if swallowed by regions where the laws of physics as we know them break down completely. One theory proposes that beneath the fractured crust lies an ocean of free-floating neutrons, behaving like a frictionless quantum fluid. When vibrations hit this zone, they might trigger cascades of nuclear reactions, miniature supernovas under the surface. This could explain why some flares contain unexpected elements like gold and platinum, forged in moments under pressures impossible to replicate on Earth. The practical implications are staggering. If we could harness even a fraction of the energy released in a single, it could power human civilization for centuries. More tantalizing is what these events teach us about material science. The crust of a magnetar represents the strongest known material in the universe, yet it still shatters. Understanding why could revolutionize everything from fusion reactor design to earthquake prediction. Perhaps most mind-bending is the time dilation effect near these objects. A lasting milliseconds from our perspective might unfold in slow motion from the perspective of someone, hypothetically, standing on the surface, stretched by the magnetar's gravity. This extreme environment is the closest thing we have to a real-world test of predictions about time warping under immense gravitational fields. Every detected adds another piece to this cosmic puzzle. Recent observations suggest some magnetars might experience aftershocks days or weeks after the initial rupture, behavior eerily similar to terrestrial earthquakes, but operating under physics we're only beginning to grasp. As our telescopes grow more sensitive, we're catching glimpses of even stranger phenomena. Whispers of vibrations that seem to originate from inside the magnetar's core, where matter may exist in forms beyond our current classification. What began as a curiosity, flashes of gamma rays from distant space, has become a window into realms where matter, energy, and time itself behave in ways that challenge our fundamental understanding of reality. And with each new observation, we're not just learning about magnetars. We're decoding the universe's most extreme physics manual, written in the language of. Among the many cosmic riddles magnetars present, none captivates the imagination like their connection to fast radio bursts, those enigmatic blips of energy that flash across the universe in less time than it takes to blink. These fleeting signals, lasting mere milliseconds, pack more energy than the sun emits in days, and some trace back directly to these magnetic monsters. The discovery that at least some FRBs originate from magnetars sent shockwaves through the astronomy community, transforming what was once speculative into something startlingly real. But what exactly happens when a magnetar unleashes one of these bursts? Picture a cosmic whip crack. The star's magnetic field lines, stretched to breaking point, suddenly snap and recoil. This violent release sends a shockwave plowing through surrounding plasma at near light speed, accelerating particles until they emit a coherent beam of radio waves intense enough to pierce entire galaxies. The resulting FRB travels billions of light years, arriving at our telescopes as a pulse so clean and powerful it seems almost engineered. This precision fuels one of astrophysics' most tantalizing debates. Could some FRBs be artificial? While most align with natural magnetar activity, a handful exhibit patterns that defy easy explanation. Some repeat at irregular intervals, while others display spectral features unlike any known astrophysical process. The infamous FRB 1212, for instance, pulses with a mathematical regularity that mirrors prime numbers, a pattern found in human-designed communication systems. It's no wonder some scientists cautiously entertain the possibility that we might be eavesdropping on alien technology, though the overwhelming consensus still points to natural origins. What makes magnetar-generated FRBs invaluable is their role as cosmic messengers. Each burst carries imprints of the material it traversed, like a fingerprint left on light. By analyzing how these signals disperse, we've mapped previously invisible filaments of plasma drifting between galaxies. Some bursts even exhibit a curious echo effect, suggesting they've warped around massive objects, potentially offering a new way to detect dark matter. The practical implications are staggering. If we could decipher the physics behind FRBs, we might unlock revolutionary communication technologies. Imagine harnessing magnetar-like pulses to transmit data across interstellar distances at nearly no energy loss, a breakthrough that could make interstellar networking feasible. Already, projects like Breakthrough Listen scan FRBs for artificial patterns, while others study how to mimic their efficiency in human-made systems. Yet for all their promise, FRBs remind us how much we don't know. Why do some magnetars produce them while others stay silent? How can such brief events release such colossal energy? Every new detection peels back another layer of mystery, revealing a universe far stranger than we ever imagined. Whether natural or engineered, these bursts are rewriting the rules of high-energy astrophysics, and magnetars hold the key to decoding them. If could see what magnetars do to spacetime, even he might be stunned. These cosmic monsters don't just have strong magnetic fields, they twist the fabric of reality itself. Near a magnetar's surface, the pull of gravity combines with unimaginable magnetic forces to create conditions where light doesn't travel in straight lines and time slows to a crawl. It's as if space becomes a funhouse mirror, warped so severely that the usual rules of physics start to break. Take something as simple as a beam of light passing near a magnetar. Instead of zipping straight through space, that light gets bent and diverted, as if space itself were a stretchy rubber sheet sagging under an immense weight. This effect, called gravitational lensing, happens around all massive objects, but around magnetars it's amplified to extremes. Photons don't just curve slightly, they can get trapped in spirals, forced into loops by the magnetar's grip. Some theories suggest that under these conditions, light might even split into different energies, creating bizarre spectral echoes we've never seen elsewhere in nature. Then there's time dilation, the slowing of clocks near intense gravitational fields. Predicted this over a century ago, and we've measured it around Earth and even the Sun. But near a magnetar, time doesn't just slow down, it crawls. A single second for someone, hypothetically, surviving on the surface could stretch into minutes or hours for an outside observer. This isn't just a thought experiment. we've detected these distortions in the pulses of radiation from magnetars. Their X-ray flickers arrive at our telescopes stretched and warped, carrying the fingerprints of warped spacetime. What makes these observations so groundbreaking is that they push relativity to its breaking point. The equations still hold, but magnetars create environments so extreme they reveal effects too subtle to detect anywhere else. For instance, some models predict that a magnetar's magnetic field could actually twist spacetime like a corkscrew, creating a phenomenon called frame dragging on a scale never before observed. If confirmed, this would be the ultimate validation of general relativity, but it might also hint at something deeper, physics beyond theories. The most tantalizing possibility: magnetars could be our first glimpse of quantum gravity, the elusive theory that would unite relativity with quantum mechanics. Near their surfaces, gravity and magnetism become so strong that quantum effects normally hidden at microscopic scales might start influencing the cosmos. Some physicists speculate that under these conditions, spacetime itself might become granular, like a digital image zoomed in too far. If we could detect this graininess, it would rewrite our understanding of reality's fundamental structure. Every flicker of light from these cosmic anomalies is a coded message about how space, time, and magnetism intertwine under conditions we can't recreate. They're not just dead stars. They're nature's most extreme physics labs, bending the universe's rules right before our eyes. And with each new observation, we're not just testing ideas, we're peering into realms where even his genius couldn't predict what we'd find. Hidden among the cosmos' most violent phenomena lies a paradox. Magnetars wield the power to annihilate life across interstellar distances, while simultaneously forging the very elements that make life possible. A single flare from one of these objects, if pointed directly at Earth within 10,000 light-years, could unleash a barrage of X-rays and gamma rays powerful enough to ionize our atmosphere. Within hours, the protective ozone layer would erode like paper in fire, exposing all surface life to deadly solar radiation. Historical mass extinctions pale in comparison to what such an event could trigger. Yet without these same cosmic cataclysms, the universe might never have developed the building blocks for planets, oceans, or organic molecules. This duality makes magnetars both architects and wrecking balls of cosmic evolution. When a magnetar erupts, the energy release isn't just destructive, it's creative. The extreme temperatures and pressures in these flares act as natural particle accelerators, slamming atomic nuclei together with enough force to forge heavy elements like gold, platinum, and uranium. These newly minted atoms get blasted into space by the explosion's shockwaves, eventually seeding molecular clouds where new stars and planets form. The gold in your jewelry might have originated in a magnetar flare billions of years before our solar system existed. The mechanics behind these apocalyptic yet fertile eruptions are staggering. During a giant flare, the magnetar's twisted magnetic field lines suddenly reconfigure, a process called magnetic reconnection. This releases energy equivalent to 1 billion hydrogen bombs detonating simultaneously, accelerating particles to near light speed. Some models suggest these flares create temporary hot spots, where temperatures exceed 10 trillion degrees, briefly hotter than the universe has been since the Big Bang itself. At these energies, even the vacuum of space bubbles with virtual particles popping in and out of existence, providing raw material for exotic nuclear reactions. Astoundingly, we've witnessed the aftermath of such events in our galactic neighborhood. In 2004, a magnetar flare from 50,000 light-years away briefly the full moon in gamma rays, despite being halfway across the Milky Way. Had it occurred within even a tenth of that distance, the radiation could have triggered a global environmental catastrophe. Yet that same flare enriched nearby nebulae with rare isotopes now detectable in meteorites. This destructive creative cycle isn't unique to magnetars. It mirrors the universe's grand pattern. Supernovas sterilize worlds while dispersing life's essential elements. Black holes shred stars while energizing star formation in their galaxies. Magnetars simply take this duality to extremes, reminding us that cosmic violence and cosmic generosity are often two sides of the same coin. Their flares may pose one of the universe's most underappreciated existential risks, but they also represent nature's ultimate alchemy labs, transforming simple matter into the complex chemistry that makes our existence possible. The deeper question isn't whether magnetars are destroyers or creators, but whether life could exist without them. Every carbon atom in our bodies was forged in stellar explosions, every heavy metal in Earth's crust distilled in cosmic catastrophes. As we search for life elsewhere in the universe, we might need to thank these terrifying yet indispensable monsters for making biology possible at all. Beneath the fractured crust of a magnetar lies a realm that defies everything we know about matter, a churning, hyperactive ocean where the rules of physics as we understand them cease to apply. This isn't water or lava or even plasma. It's a quantum soup of superfluid neutrons and superconducting protons, flowing without friction at temperatures near absolute zero, yet under pressures so intense they'd crush Earth into a marble. Imagine liquid metal, but one where the very concept of viscosity has been erased by quantum mechanics, and where electric currents never fade, looping endlessly through the star's core. This bizarre interior isn't just a curiosity. It's the engine that powers a magnetar's apocalyptic magnetic fields, and it might hold the blueprint for revolutionary technologies here on Earth. What makes this quantum ocean so extraordinary? Start with the neutrons. Under normal conditions, these particles stick together in atomic nuclei. But inside a magnetar, gravity rips apart those structures, creating a sea of free neutrons so dense that a single drop would weigh billions of tons. Yet despite this density, quantum effects allow these neutrons to flow without resistance, forming a superfluid that can literally climb the walls of its own container. Picture molasses turning into a frictionless gas, except here, it's happening with matter compressed to nuclear density. Meanwhile, the protons in this soup pair up and conduct electricity with perfect efficiency, creating persistent currents that generate magnetic fields dwarfing anything possible in our laboratories. The real magic happens when these two states interact. As the superfluid neutrons swirl, they drag the superconducting protons along with them, twisting magnetic field lines like strands of cosmic spaghetti. This dynamo effect amplifies the star's magnetic field to ludicrous strengths, but it's a delicate balance. Too much motion, and the proton's superconducting state can abruptly collapse, releasing stored energy in catastrophic flares. Think of it like a hydroelectric dam where the water is also the turbine, and the walls are made of unstoppable force. Why does this matter for us? Because hidden in this chaos are clues to creating room temperature superconductors, materials that could revolutionize energy transmission, medical imaging, even quantum computing. For decades, physicists have struggled to replicate superconducting effects outside extreme laboratory conditions. Yet inside every magnetar, nature has already solved the puzzle, sustaining superconductivity under pressures that should, by all rights, destroy it. The secret might lie in how protons pair up in these environments, forming structures called Cooper pairs that persist despite the surrounding turmoil. If we could decode this mechanism, it might lead to materials that carry electricity without loss, eliminating power grids' inefficiency, or enabling floating trains that glide on magnetic fields. Even more tantalizing is the potential for quantum computing. Magnetar interiors exhibit quantum phenomena on macroscopic scales, with trillions of particles acting in unison, precisely the kind of coherence we struggle to maintain in qubits. Some researchers speculate that studying magnetar dynamics could reveal how to scale up quantum systems without them collapsing into decoherence. It's as if the universe hid an instruction manual for next-generation technology inside its most violent objects. Yet for all its promise, this quantum ocean remains frustratingly out of reach. We can't probe it directly. No probe could survive the crushing gravity or lethal radiation. Instead, we rely on indirect clues, the way magnetars vibrate after, the energy spectra of their flares, even subtle changes in their spin rates. Each observation is like trying to reconstruct a symphony by listening to echoes bouncing off a distant canyon wall. What's clear is that magnetars aren't just cosmic oddities. They're living experiments in extreme quantum mechanics. Their interiors represent a state of matter that can't exist naturally anywhere else in the universe, governed by physics we're only beginning to grasp. Every flicker of light from these distant monsters carries encrypted messages about how matter behaves under conditions we'll never replicate on Earth. And if we can learn to read them, they might just hand us the keys to technologies that sound like science fiction today. Among the most tantalizing possibilities about magnetars is their potential role in uncovering dark matter, the invisible substance that makes up 85% of the universe's mass yet stubbornly refuses to interact with light. While physicists have built underground labs, particle colliders, and space telescopes in pursuit of this cosmic ghost, nature may have already provided the perfect dark matter detector: a spinning, hypermagnetic neutron star. The theory goes like this: if dark matter particles occasionally collide with a magnetar's dense core, the resulting energy release could create subtle but detectable disturbances in the star's radiation patterns. It's as if these cosmic lighthouses might flicker in ways that betray the presence of invisible matter passing through them. Why magnetars? Their extreme environments amplify effects that would be imperceptible anywhere else. Picture a dark matter particle drifting through ordinary space. It would zip past stars and planets like a bullet through fog, leaving no trace. But inside a magnetar, where gravity compresses matter to nuclear density and magnetic fields trap particles with incredible efficiency, even a fleeting interaction could ripple outward. Some models suggest that certain types of dark matter, hypothetical particles called axions or WIMPs, could convert into detectable photons when exposed to a magnetar's monstrous magnetic field. These photons would carry distinct signatures in their energy levels, like cosmic breadcrumbs leading us to dark matter's doorstep. The search hinges on anomalies, unexplained dips or spikes in magnetars' X-ray emissions that don't match known physics. In 2020, astronomers studying a magnetar 21,000 light-years away spotted a peculiar burst followed by rhythmic X-ray pulses unlike any stellar activity previously recorded. One interpretation: a clump of dark matter particles, drawn in by the magnetar's gravity, briefly altered the star's internal quantum oscillations before being annihilated by the intense environment. While not conclusive, such events offer a roadmap for where to look next. What makes this approach revolutionary is its scale. Traditional dark matter detectors on Earth are painstakingly sensitive, buried deep underground to shield from interference. A magnetar, by contrast, is nature's ultimate particle accelerator, its core conditions so extreme they magnify dark matter interactions by factors of trillions. Instead of waiting years for a single candidate event in a lab tank, astronomers could monitor magnetars for patterns across light years, turning the entire galaxy into a dark matter observatory. The implications stretch beyond detection. If magnetars do reveal dark matter's properties, we might finally understand how it shaped the universe's structure. Some theories suggest dark matter could accumulate in magnetars' cores over time, subtly altering their rotation rates or even triggering. This would mean these stars aren't just passive detectors. They're actively wrestling with the universe's hidden architecture, their violent flares possibly echoing the unseen battles between ordinary and dark matter. Yet challenges remain. Distinguishing dark matter signals from magnetars' already chaotic behavior requires precision measurements of their spin, temperature, and magnetic field strength, a task pushing our current telescopes to their limits. Future observatories like the Square Kilometer Array Radio Telescope or the Athena X-ray mission could provide the needed resolution. Until then, every strange pulse from these magnetic monsters keeps alive the electrifying possibility that we're glimpsing the invisible scaffolding of reality itself. Magnetars don't just live forever. They evolve in ways that challenge our understanding of stellar life cycles. Unlike ordinary stars that fade into dim embers or explode dramatically, these magnetic monsters face a far stranger fate. Some may quiet down over, their apocalyptic magnetic fields gradually dissipating until they become ordinary neutron stars. Others might meet a more violent end, cracking apart under their own internal stresses or collapsing into something even more exotic. The most tantalizing possibility, they could transform into quark stars, hypothetical objects where neutrons themselves break down into their fundamental components, rewriting the rules of matter as we know it. Tracking a magnetar's aging process is like watching time-lapse footage of cosmic decay, except in extreme slow motion. Observations reveal that younger magnetars spin faster and flare more violently, while older ones gradually slow down, their eruptions becoming less frequent but sometimes more intense. This suggests their magnetic fields aren't static, they're decaying, but not in any predictable way. Some exhibit sudden glitches, spinning faster for reasons we don't fully understand, as if something inside them is rearranging. Others simply fade into radio silence, leaving us to wonder whether they've shut down permanently or are just gathering energy for another outburst. The real mystery is what happens when a magnetar's internal pressure crosses a critical threshold. Under enough strain, the neutrons in its core, already packed than in any lab experiment, might shatter into quarks, the building blocks of all matter. If this happens, the star could contract even further, becoming a quark star, an ultradense object where matter exists in a state unlike anything else in the universe. Think of it as cosmic alchemy, neutrons dissolving into a soup of free-floating quarks, bound by forces so strong they create a new phase of matter. Some theories suggest quark stars might emit distinct gravitational waves or neutrino bursts, giving us ways to hunt for them. But the most dramatic end for a magnetar could be an explosion so powerful it makes a supernova look like a firecracker. If a magnetar's core collapses into a black hole, the sudden release of magnetic energy might trigger a cataclysm visible across the universe. There's even speculation that some gamma-ray bursts, the most energetic event since the Big Bang, could be dying magnetars tearing themselves apart. The afterglow of these explosions might carry signatures of the star's magnetic field, like a cosmic fingerprint revealing its final moments. What makes studying there so crucial is that magnetars could be showing us the ultimate fate of matter under conditions we can't recreate. If they do transition into quark stars, it would prove that neutron-rich matter isn't the final state. There's something denser, stranger waiting beyond. And if they explode, they might seed the cosmos with rare elements forged in their cores. These aren't just stellar corpses, they're time capsules, preserving clues about how the universe recycles matter on the grandest scales. Every flicker, every flare, every slowdown is a piece of the puzzle, one that might reveal not just how magnetars die, but how the fabric of reality itself behaves under pressures beyond imagination. If you could hear a magnetar, it would sound like nothing in our world. a haunting chorus of ultra-low rumbles and piercing high-frequency shrieks, vibrating at pitches no human ear could naturally detect. Scientists convert these oscillations into audible sound by dramatically slowing them down, revealing a cosmic symphony that defies imagination. The result, a deep, resonant hum punctuated by sudden cracks and pops, like an enormous cello being plucked by invisible fingers while submerged in liquid nitrogen. These aren't random noises. They're the literal vibrations of a star's crust twisting under forces powerful enough to snap spacetime itself. What makes these star songs so valuable is how they expose secrets hidden beneath the Magnetar's surface. Just as geologists use earthquakes to map Earth's interior, astrophysicists analyze these vibrations to probe regions we'll never see directly. Each frequency corresponds to different layers. The deeper the tone, the further down it originates. Some oscillations spiral outward like ripples on a pond, while others bounce between the star's poles, trapped by the curvature of its monstrous magnetic field. The patterns are so distinct that researchers can pinpoint where it occurred, whether near the equator or deep beneath the crust, just by listening. The most startling discovery came when astronomers realized some magnetars emit near-perfect harmonic frequencies, mathematically pure tones that resemble the notes of a finely tuned instrument. One particular magnetar, observed in 2007, produced vibrations at 293 Hz, almost exactly the D note on a piano. This wasn't random noise. It was evidence of a perfectly symmetrical rupture, as if the star's crust had fractured along geometric fault lines. Such precision in chaos suggests an underlying order to magnetars, violence, hinting at crystalline structures beneath their surfaces that vibrate like cosmic tuning forks. But the real breakthrough came when scientists noticed missing frequencies, gaps in the vibrational spectrum where certain tones simply didn't appear. These absences turned out to be even more revealing than the sounds themselves. Just as a Stradivarius violin's unique shape filters specific notes, a magnetar's interior absorbs certain vibrations, betraying the presence of exotic phenomena. Some theories propose these silent zones might mark where the star's superfluid core meets its solid crust, creating a boundary so extreme it swallows vibrations whole. Others suggest the gaps could be signatures of dark matter accumulating in the magnetar's core, damping specific frequencies as it interacts with the star's quantum soup. The implications stretch far beyond astrophysics. By refining these acoustic techniques, researchers are developing new ways to study extreme materials here on Earth. The same algorithms used to decode magnetar vibrations now help engineers detect microscopic cracks in nuclear reactors or analyze seismic signals from underground explosions. It's as if these distant stars have handed us a new form of sonar, one that works across light years and under conditions no lab could ever replicate. Perhaps most poetic is how these sounds bridge the gap between human experience and cosmic wonder. A magnetar's oscillations, translated into sound, become something we can feel in our bones, a visceral reminder that the universe isn't just something we see, but something we might one day hear. And as our telescopes grow more sensitive, we're not just observing these stars, we're learning to listen to them, uncovering rhythms in their violence that whisper secrets about the deepest laws of physics. Among the most radical ideas in modern physics is the notion that our universe might not be alone, that hidden dimensions or alternate realities could exist just beyond our perception. Normally, these concepts remain trapped in chalkboard equations, impossible to test. But magnetars, with their space-time warping gravity and physics-defying magnetic fields, might be nature's way of prying open cracks in reality's foundation. At the boundary where their immense gravity meets quantum uncertainty, some theories suggest we could find evidence of parallel universes, extra dimensions, or even clues that our cosmos is a holographic projection. Consider string theory's bold proposal that the universe operates not just in 3 spatial dimensions, but in 10 or more, with the extra dimensions curled up too tightly to detect. Near a magnetar's surface, where gravity distorts the fabric of spacetime like a funhouse mirror, these hidden dimensions might stretch just enough to leave faint fingerprints. Certain vibrational modes in Magnetar, for example, could carry energy signatures that don't match any known particle, hinting at energy leaking into or out of other dimensions. It's like tapping on a wall and hearing an echo from a room you never knew existed. Even more mind-bending is the holographic principle, the idea that our 3-dimensional universe might actually be encoded on a 2-dimensional surface at its boundary, like a cosmic version of a hologram sticker. Magnetars, with their ability to twist spacetime into knots, could act as natural amplifiers for this effect. Their magnetic fields might interact with the quantum foam of space in ways that reveal pixel-like structures in reality itself, tiny bits of spacetime that only become visible under extreme conditions. Imagine zooming in on a digital photo until you see the individual pixels. Magnetars could be providing that same zoom lens for the universe's underlying code. Some researchers speculate that Magnetar Flares aren't just electromagnetic events. They could be moments where our universe briefly brushes against another. In these collisions, energy might transfer between dimensions, explaining why some bursts release more energy than seems physically possible in our universe alone. It's as if these stars are cosmic buoys, bobbing on the boundary between realities, occasionally sending ripples across the divide. The most tantalizing evidence comes from anomalies in gamma-ray polarization, the orientation of light waves from Magnetar Flares. Certain patterns detected in recent observations don't align with standard physics, but they match predictions of how light would behave if it had traversed hidden dimensions or interacted with exotic particles from parallel universes. While still speculative, these measurements have sparked serious discussions about using magnetars as portals to test theories that were once purely philosophical. What makes this search so revolutionary is its practicality. Instead of waiting for futuristic particle colliders or space telescopes, we might already have the tools to probe the multiverse by studying the violent twitches of these dying stars. Every unexplained spike in a magnetar's radiation, every odd vibration in its crust, could be a message from beyond our dimensional horizon. And if we learn to decode them, we might finally answer one of humanity's oldest questions. Are we alone in the cosmos? Or is our universe just one page in an infinite book of realities deep in the violent hearts of colliding magnetars? Nature runs the universe's most exclusive jewelry workshop, one where the forces required to forge gold and platinum would make even the most advanced particle accelerators look like children's toys. When these ultradense stellar remnants slam together or erupt in cataclysmic flares, they create conditions so extreme they can transform ordinary matter into rare, heavy elements in seconds. The temperatures briefly exceed 10 trillion degrees, hotter than the core of a supernova, while pressures reach levels where atomic nuclei get crushed together like grapes in a cosmic vice. This isn't just alchemy, it's the universe's ultimate smelting process, and it might explain why Earth's crust contains traces of precious metals that shouldn't exist here naturally. The secret lies in a phenomenon called rapid neutron capture, or the R process. Under normal stellar conditions, creating elements heavier than iron requires more energy than it releases, like trying to build it in a hurricane. But during a magnetar collision or flare, the environment becomes so neutron-rich that atomic nuclei get bombarded with free neutrons at unbelievable rates. Imagine throwing marbles into a speeding blender. The neutrons stick to seed nuclei faster than the resulting atoms can decay, building up heavier and heavier elements in a chaotic chain reaction. In less time than it takes to snap your fingers, a single magnetar event can produce its weight in gold, platinum, and other rare metals before blasting them into space at near light speed. We've actually detected the aftermath of this cosmic minting process. In 2017, astronomers witnessed two neutron stars colliding 130 million light-years away, an event that shook spacetime itself with gravitational waves. Follow-up observations revealed something astonishing: signatures of newly forged gold and platinum in the explosion's afterglow. Calculations suggested this single event produced over 10 times Earth's mass in gold alone, scattering it across interstellar space. While not all neutron stars are magnetars, the presence of ultra-strong magnetic fields in such collisions could supercharge the ARP process, making magnetar encounters even more efficient cosmic forges. This raises a fascinating possibility: that the gold in your wedding ring or smartphone might have originated in a magnetar cataclysm billions of years before our solar system formed. These precious atoms, forged in violence, likely drifted through space for eons before getting swept up in the molecular cloud that birthed our sun and planets. It's poetic to think that the rarest elements on Earth trace back to the most extreme events in the cosmos, a direct material link between human civilization and the universe's most destructive forces. But the implications stretch far beyond jewelry. Understanding magnetar-driven nucleosynthesis could revolutionize how we mine precious metals in the future. Some scientists speculate that ancient neutron star collisions might have left concentrated deposits of heavy elements in certain regions of space, interstellar gold fields waiting to be harvested. Projects like NASA's upcoming mission aim to map the distribution of these elements across the Milky Way, essentially creating a treasure map of cosmic proportions. While asteroid mining gets all the attention, the real jackpot might lie in identifying stellar remnants enriched by magnetar activity. The most tantalizing prospect: we might someday replicate magnetar conditions in controlled experiments. Recent breakthroughs with high-power lasers and magnetic confinement devices have allowed physicists to momentarily recreate the temperatures and densities of neutron star surfaces. While we're still centuries away from producing meaningful amounts of synthetic gold, each step forward reveals more about how the universe's most exotic objects became the ultimate chemists, transforming the debris of dead stars into the building blocks of everything from cell phones to cathedral domes. What began as a puzzle, why rare metals exist in Earth's crust at all, has blossomed into one of astrophysics' most surprising narratives. Magnetars aren't just destroyers, they're cosmic artisans, weaving heavy elements into the fabric of galaxies. Their collisions serve as reminders that the universe's most valuable resources often emerge from its most violent events, a lesson written in stardust and atomic fire. Hidden in the extreme conditions of a magnetar's core may lie one of physics' most sought-after holy grails, the quantum critical point. This is the theoretical tipping point where matter stops behaving according to classical rules and enters a state of pure quantum chaos, where electrons don't just flow but organize into patterns we've never seen before. Under normal conditions, materials transition smoothly between phases, like ice melting into water. But at the quantum critical point, these transitions become abrupt and unpredictable, creating matter that defies all conventional classification. Magnetars, with their crushing gravity and unimaginable magnetic fields, could be nature's only natural laboratories where this phenomenon occurs spontaneously. The implications are staggering. At the quantum critical point, electrons become strongly correlated, meaning they stop acting as individual particles and begin moving in perfect synchronized formations. This collective behavior is exactly what gives rise to high-temperature superconductivity, where electricity flows without resistance. On Earth, we've struggled for decades to achieve this state outside specialized lab conditions. Yet inside every active magnetar, nature may have already solved the puzzle, maintaining superconductivity at temperatures and pressures that would vaporize any known material. If we could decode how this works, it might lead to power grids with zero energy loss, ultra-efficient quantum computers, or even revolutionary propulsion systems. What makes this state so elusive is its paradoxical nature. Normally, increasing temperature destroys orderly quantum effects. That's why superconductors require extreme cooling. But at the quantum critical point, rising temperatures can actually enhance quantum coherence instead of disrupting it. Magnetars likely achieve this delicate balance through their insane magnetic fields, which force particles into alignment despite the thermal chaos around them. Picture trying to organize marbles on a vibrating table. Impossible under normal circumstances, but feasible if you had a powerful magnet underneath, pulling them into formation regardless of the shaking. Recent observations provide tantalizing clues. Some magnetars exhibit strange glitches in their rotation, sudden speedups that can't be explained by standard physics. One compelling theory suggests these occur when pockets of the star's interior briefly reach the quantum critical point, causing whole regions to switch between superconducting and normal states. The energy released in these transitions could nudge the entire star's rotation, like a spinning ice skater suddenly pulling their arms inward. These glitches might be our first direct evidence of quantum criticality in action, written in the language of stellar mechanics. The potential applications on Earth are mind-bending. Materials operating near their quantum critical point exhibit properties that seem almost magical. Some become perfectly transparent to magnetic fields, while others develop memory, where their structure changes based on past exposures. A magnetar-inspired breakthrough could lead to computers that process information using quantum critical states, potentially solving problems in seconds that would take conventional machines. Or imagine medical imaging where quantum critical sensors detect tumors at the single-cell level by spotting infinitesimal magnetic disturbances. Yet the greatest prize might be solving one of condensed matter physics' longest-standing mysteries, why some materials suddenly become superconductors at relatively high temperatures. For 40 years since the discovery of copper-based superconductors, we've lacked a complete theory explaining this phenomenon. Magnetars, by demonstrating how quantum criticality emerges under extreme conditions, could provide the missing blueprint. It's as if the universe hid the key to room temperature superconductivity inside its most violent objects, waiting for us to decipher their quantum whispers. As we develop more sensitive X-ray telescopes and gravitational wave detectors, each new observation peels back another layer of this cosmic enigma. The answers won't just rewrite physics textbooks. They could spark a technological revolution, turning science fiction into reality. And all of it hinges on decoding how matter behaves when pushed beyond all known limits, in the heart of nature's most extreme quantum crucibles. Some magnetars are the universe's oldest living relics, stellar fossils that have witnessed nearly the entire history of existence. Born within 1 billion years of the Big Bang, these ancient objects are more than just cosmic oddities. They're perfectly preserved snapshots of the early universe, frozen in time by their unimaginable density and magnetic might. Unlike stars that burn out or black holes that consume their past, magnetars lock away secrets from an era when galaxies were just beginning to form, and the cosmos was a chaotic nursery of raw energy and matter. Studying them is like unearthing a time capsule sealed at the dawn of creation. one that holds clues about how the universe evolved from a seething plasma into the structured expanse we see today. What makes these primordial magnetars so special? Their extreme environments act as natural deep freezers, slowing atomic motion to a near standstill and effectively pausing the decay processes that would erase evidence elsewhere. The magnetic fields threading through them are so strong they trap particles in quantum states that haven't existed naturally since the universe's first seconds. It's as if these stars captured a piece of the early cosmos in amber, except instead of tree resin, the preservative is a magnetic grip powerful enough to bend spacetime itself. One of the most tantalizing possibilities is that these ancient magnetars might contain traces of hypothetical particles from the universe's infancy. Relics like magnetic monopoles or strange quark matter that theorists predict should have formed in the extreme heat of the Big Bang, but have never been observed. If such particles were frozen into a magnetar structure during its birth, their subtle influence could subtly alter the star's vibrations or radiation patterns in ways we're just learning to detect. Imagine finding a dinosaur bone with intact DNA. These stars offer the astrophysical equivalent, preserving physics that otherwise vanished 14 billion years ago. The way these objects spin tells its own story. Younger magnetars rotate dozens of times per second, but the oldest ones have slowed to a crawl, completing a single revolution every 10 seconds or more. This glacial pace isn't just a sign of age, it's a record of the universe's changing conditions. By comparing their spin rates to those of younger magnetars, astronomers can reconstruct how the density of the early cosmos affected stellar rotation, much like tree rings reveal past climates. Some of these ancient spinners even exhibit peculiar wobbles, possibly caused by interactions with dark matter particles that were far more abundant in the early universe. But the real treasure lies in their light. When a magnetar flares, the radiation it emits carries spectral fingerprints of the elements surrounding it at birth. Recent observations of one elderly magnetar revealed an unexpected abundance of primordial helium and almost no heavier elements, a composition matching theoretical predictions of the universe's chemical makeup just minutes after the Big Bang. This star isn't just old, it's a pristine sample from a time before supernovae polluted the cosmos with metals, offering a direct look at the universe's original recipe. The implications stretch beyond astrophysics. If we can decode the conditions preserved in these cosmic time capsules, we might finally answer why matter triumphed over antimatter in the early universe, or why dark energy began dominating cosmic expansion billions of years later. These aren't just scientific curiosities, they're the foundational mysteries of existence itself, and magnetars might hold the keys. Every flicker from these ancient sentinels is a message from the past, written in the language of extreme physics and waiting for us to translate it. In the universe of extremes, where magnetars reign as kings of magnetic might, there exists a puzzling anomaly, the antimagnetars. These cosmic misfits are neutron stars that defy expectations, sporting magnetic fields thousands of times weaker than their hypercharged cousins. At first glance, they seem almost ordinary, like quiet neighbors in a neighborhood of screaming supernovas. But their very existence throws a wrench into our understanding of how stellar remnants evolve. If magnetars are the universe's overachievers, antimagnetars are the enigmatic underdogs, hiding secrets about the hidden pathways stars take after death. What makes these objects so baffling is that they shouldn't exist, at least, not according to textbook astrophysics. When a massive star collapses into a neutron star, its magnetic field ought to amplify dramatically, squeezed and twisted by the star's rapid contraction. Yet antimagnetars somehow sidestep this process, emerging with fields barely stronger than Earth's. One leading theory suggests their magnetic energy might have leaked away over time, drained by some unseen cosmic siphon. Picture a battery left out in the rain, except in this case, the rain is a quantum process where magnetic energy transforms into heat or neutrinos, slowly bleeding the star of its power. Another possibility is even more radical. These stars might have been born different. While most neutron stars inherit their magnetic fields from the parent star's core, anti-magnetars could form through an alternative route, perhaps when a dying star's magnetic field gets tangled and cancels itself out during collapse. Imagine crumpling a sheet of paper covered in arrows pointing every direction. When you crush it into a ball, the arrows might neutralize each other, leaving no dominant alignment. If true, this would mean neutron stars have multiple birth channels, like cosmic twins separated at creation. The most intriguing antimagnetar might be the one lurking right in our cosmic backyard. The neutron star at the heart of the Cassiopeia, a supernova remnant, spins rapidly, but has a mysteriously weak magnetic field. Some researchers speculate it could be transitioning into a new state, a sort of zombie magnetar that exhausted its magnetic fury long ago. Others wonder if it's proof of an entirely new class of stellar remnant, one that evolves differently from the neutron stars we know. Every pulse of X-rays from this object carries clues, as if it's whispering its life story in a code we're still learning to crack. What antimagnetars teach us is that the universe loves variety. Just as some stars explode violently while others fade quietly, neutron stars seem to have their own destinies, some becoming magnetic titans, others fading into obscurity. This diversity might hold the key to understanding why certain neutron stars power brilliant pulsars while others vanish into darkness. The more we study these quiet outliers, the clearer it becomes. The cosmos doesn't follow a single script. It improvises, experiments, and occasionally leaves us scratching our heads in wonder. Some of the most energetic particles in the universe might owe their existence to magnetars, cosmic accelerators capable of flinging matter across galaxies at nearly the speed of light. These aren't just any particles. They're ultra-high-energy cosmic rays, atomic fragments packing enough punch to rival a major league fastball, except compressed into a single subatomic speck. When these microscopic bullets rain down on Earth's atmosphere, they trigger cascades of secondary particles, leaving faint trails that have baffled scientists for over a century. Where do such powerful projectiles come from? The answer might lie in the violent neighborhoods surrounding magnetars, where physics gets stretched to its absolute limits. Picture the environment around one of these magnetic monsters. A chaotic zone where twisted field lines snap like overtensioned cables, releasing enough energy to accelerate protons and atomic nuclei to velocities approaching light speed. The mechanism works like nature's own particle collider, but with power levels that dwarf anything humans have built. As magnetar flares erupt, they create shockwaves in the surrounding plasma, acting like cosmic surfboards that particles can ride to unimaginable energies. Some models suggest these shocks might work in stages, each one giving particles an additional boost until they're hurled into space with energies exceeding 100 billion electron volts. To put that in perspective, that's millions of times more energy than the Large Hadron Collider can produce, all generated naturally by a single star's magnetic tantrum. The real smoking gun came in 2021 when astronomers traced several ultra-high-energy cosmic rays back to regions harboring known magnetars. These particles carried distinct signatures, an overabundance of certain atomic nuclei and peculiar energy distributions that matched theoretical predictions of magnetar acceleration. It was like finding gunpowder residue on a suspect's hands. The evidence pointed squarely to these magnetic powerhouses as at least one source of the universe's most energetic particles. But the mystery deepens when you consider the journey these particles undertake. Cosmic rays from magnetars don't travel in straight lines. their paths get scrambled by interstellar magnetic fields, turning space into a giant pinball machine. By the time they reach Earth, their origins are obscured, forcing scientists to play detective with subtle clues in their composition. Some arrive with telltale traces of heavy elements like iron or silicon, suggesting they were torn from the Magnetar's crust during a. Others show damage patterns indicating they've been battered by intense radiation, as if they barely escaped the star's lethal grip. Each particle becomes a tiny time capsule, preserving a record of the extreme conditions that launched it across the cosmos. What makes this discovery so revolutionary isn't just solving an old puzzle, it's opening new doors to understanding the universe's particle budget. If magnetars contribute significantly to cosmic rays, they might also be responsible for seeding galaxies with the raw materials for star formation. Every time a magnetar flare hurls heavy elements into space, it enriches interstellar clouds with the building blocks for future planets and life. These violent events aren't just destructive, they're part of a grand recycling program, scattering stardust that might one day end up in a newborn solar system. Yet questions remain. Why do some magnetars appear to produce cosmic rays while others do? Could there be an even more powerful class of cosmic accelerator we haven't identified? And what happens when these ultra-energetic particles collide with Earth's atmosphere? Could they pose risks we're only beginning to understand? As detectors like the Pier Auger Observatory in Argentina capture more of these rare events, we're inching closer to answers. Each high-energy impact is a message from one of the universe's most extreme environments, written in the language of shattered atoms and twisted spacetime. Deep in the cosmos, certain magnetars perform an optical illusion so precise it challenges our understanding of how light interacts with matter. These stellar oddities don't just emit X-rays, they bounce them back into space with near-perfect efficiency, acting like celestial mirrors polished to a supernatural sheen. Unlike ordinary mirrors that reflect visible light, these cosmic reflectors deal in X-rays, the same high-energy radiation used in hospitals to scan bones or in airports to peer through luggage. The difference? A magnetar's reflective surface isn't made of glass or metal, but of plasma so densely packed and magnetically controlled that it deflects X-rays like a spoon redirects a stream of water. How does this impossible reflection work? The secret lies in the magnetar's atmosphere, a thin layer of ionized gas trapped by magnetic fields billions of times stronger than Earth's. Under normal conditions, X-rays would blast straight through such a layer, but here, the magnetic field acts like an invisible grid, forcing electrons in the plasma to vibrate in unison. When incoming X-rays hit this synchronized electron sea, they don't get absorbed, they get collectively rejected, like a crowd pushing back against a sudden shove. The result is an X-ray echo so crisp it can be detected across interstellar distances, carrying information about the magnetar's surface conditions with unprecedented clarity. One particular magnetar, cataloged as SGR 1846-29, stunned astronomers when observations revealed it reflecting nearly 90% of incoming X-rays, a feat comparable to finding a mirror in the desert that reflects sunlight more efficiently than polished silver. This discovery didn't just rewrite astrophysics textbooks, it sparked a revolution in materials science. Engineers realized that if we could mimic even a fraction of this natural X-ray reflection, it could transform technologies from medical imaging to nuclear fusion. Imagine CT scanners that deliver sharper images with lower radiation doses, or industrial X-ray machines that inspect metal welds without the blurring caused by scattered rays. The most tantalizing application might be in energy production. Modern fusion reactors struggle with containment. Their plasma tends to leak energy in the form of X-rays. But if reactor walls could be lined with magnetar-inspired reflective materials, they might bounce escaping energy back into the reaction chamber, dramatically improving efficiency. Early lab experiments with artificially generated magnetic fields have already demonstrated rudimentary X-ray reflection, proving the concept isn't just theoretical. It's as if nature handed us a blueprint for handling high-energy radiation, hidden in the behavior of its most magnetic stars. Yet the phenomenon raises deeper questions. Why do only some magnetars exhibit this mirror-like quality? Observations suggest it might depend on the angle between the star's magnetic axis and its rotation, a cosmic alignment that either creates perfect reflection or lets X-rays escape unimpeded. There's also the puzzle of how these magnetic mirrors remain stable amid the magnetar's otherwise chaotic environment, wherein flares constantly reshape the surface. Some theories propose that the reflecting layer exists in a temporary sweet spot, too tenuous to be disrupted by quakes, yet dense enough to interact with X-rays coherently. Every flicker of reflected X-ray light carries encrypted data about conditions near the magnetar's surface, offering clues we can't gather any other way. By studying these cosmic mirrors, we're not just unlocking secrets of neutron stars, we're discovering principles that could redefine how humanity harnesses some of the most powerful radiation in the universe. The same forces that make magnetars deadly might one day make our technology cleaner, safer, and unimaginably more advanced. Astronomers face a cosmic detective story with one glaring clue missing. Where are all the magnetars? Based on how neutron stars form and evolve, our galaxy should be teeming with these magnetic monsters, perhaps thousands of them. Yet we've only confirmed around 30. This glaring discrepancy isn't just a census error, it's a potential window into physics we've yet to imagine. Somewhere between the violent death of massive stars and the eerie silence of deep space, magnetars seem to vanish or transform into something we can't yet recognize. One possibility is that we're simply overlooking them. Magnetars spend most of their lives in quiescent states, emitting faint X-rays that blend into the background hum of the galaxy. Without dramatic flares or pulses to announce their presence, they could be hiding in plain sight, camouflaged among ordinary neutron stars. Recent surveys using sensitive X-ray telescopes have uncovered a handful of these quiet magnetars, their identities betrayed only by subtle irregularities in their magnetic signatures. It's like searching for a whisper in a hurricane, but new machine learning techniques are teaching telescopes to pick out these cosmic murmurs from the noise. But what if the answer isn't observational? What if magnetars truly are rare? Their scarcity might point to a special ingredient required at birth, something most collapsing stars lack. Perhaps only stars born with unusually strong magnetic fields, or those that collapse at just the right angle, can ignite the dynamo that creates magnetar-level magnetism. There's even a controversial theory that certain heavy elements in a star's core, like gold or uranium, could act as catalysts, boosting magnetic field generation during collapse. If true, this would mean magnetars aren't just stellar remnants, they're the cosmic equivalent of a perfectly struck bell, ringing only under exquisite conditions. The most intriguing hypothesis is that magnetars don't disappear, they evolve. Over their monstrous magnetic fields might gradually decay, transforming them into ordinary neutron stars. Or something far stranger could happen. Their cores could reach a tipping point where magnetism triggers a phase transition, converting them into quark stars or even exotic hybrid objects that emit no detectable radiation at all. Imagine a celestial metamorphosis, where the universe's most magnetic objects shed their extreme properties like a butterfly emerging from a cocoon, leaving behind a remnant we've never learned to identify. This mystery isn't just academic, it cuts to the heart of how matter behaves under conditions we can't replicate. Every missing magnetar represents a gap in our understanding of stellar life cycles, magnetic field generation, and even quantum mechanics. Future gravitational wave observatories might detect the collisions of hidden magnetars, while next-generation X-ray telescopes could spot their faded afterglows. Until then, their absence remains one of astrophysics' most tantalizing puzzles, reminding us that the universe still keeps its most explosive secrets well hidden. Among the wildest possibilities in theoretical physics is that magnetars, already masters of spacetime distortion, might serve as cosmic gatekeepers for wormholes. These hypothetical tunnels through the fabric of reality could, in principle, connect distant points in the universe or even different universes entirely. While wormholes remain firmly in the realm of speculation, the extreme conditions around magnetars provide a tantalizing environment where such structures might theoretically stabilize long enough to be traversable. Picture a tunnel where one end hovers near a magnetar's crushing gravity, while the other opens somewhere else entirely, perhaps another galaxy, another time, or another dimension. The key lies in the interplay between gravity and magnetism at scales we can barely comprehend. Wormholes, as predicted by equations, would snap shut instantly under normal conditions, crushed by their own instability. But a magnetar's ludicrously strong magnetic field could counteract this collapse, acting like cosmic scaffolding to prop open the throat of the wormhole. Think of it as using a powerful magnet to hold open a spring-loaded door. The magnetic energy distorts spacetime just enough to prevent the tunnel from pinching shut. Some models suggest the field lines might even twist the wormhole's interior into a helical shape, creating a natural corridor that particles, or hypothetical spacecraft, could navigate. This isn't just science fiction. The mathematics behind this idea stems from legitimate solutions to general relativity, where rotating magnetized objects create peculiar spacetime geometries. Recent simulations show that under precise conditions, a magnetar's energy could generate negative energy densities, an exotic requirement for keeping wormholes stable. The catch: these conditions are so extreme they border on the absurd. The magnetic fields needed would dwarf even a typical magnetar's already insane strength, and the alignment of rotation and magnetic axes would have to be perfect, like balancing a spinning top on the edge of a knife. Yet the implications are staggering. If such a wormhole could be artificially induced or discovered naturally, it might offer shortcuts across the cosmos. A journey that would take at light speed could become a stroll through a cosmic. Even more mind-bending is the possibility of time dilation effects near the entrance, where the wormhole's throat could connect not just places but different moments in time. Of course, the energy requirements and engineering challenges make this purely hypothetical for now. But the fact that nature might have already created the necessary conditions in magnetars is a thrilling thought. Skeptics rightly point out the hurdles. Wormholes would require forms of matter with negative energy, something we've never observed. The radiation environment near a magnetar would vaporize any known material, and the tidal forces near a wormhole's entrance would spaghetti anything attempting passage. But magnetars remind us that the universe often outdoes our imagination. Before their discovery, no one believed magnetic fields could reach such intensities. Now we know they're not just possible, they're common. Perhaps the most fascinating aspect is how magnetars blur the line between science and speculation. They're real objects that behave like theoretical constructs, pushing physics into uncharted territory every time we observe them. Whether or not wormholes ever become more than equations on a chalkboard, the fact that magnetars keep these dreams mathematically plausible is a testament to how much we still have to learn about the cosmos. Every flicker of X-rays from these magnetic monsters could be hinting at phenomena we've yet to name. Bridges across spacetime hiding in plain sight, waiting for us to recognize their potential. Even the most predictable magnetars occasionally throw scientists a cosmic curveball, sudden, unexplained speed-ups in their rotation that defy fundamental physics. These bizarre events, known as glitches, can make an already spinning magnetar rev faster in milliseconds, as if an invisible hand gave it a forceful shove. Picture a figure skater mid-spin suddenly accelerating without pulling their arms in, an impossible feat under normal conservation laws. Yet in the extreme realm of magnetars, these violations aren't just possible. They're windows into physics operating at the edge of comprehension. What triggers these glitches? One leading theory points to the magnetar's interior, where a superfluid ocean of neutrons swirls beneath a rigid crust. Under normal conditions, this superfluid rotates in sync with the crust, creating stable spin. But when quantum vortices, tiny whirlpools in the neutron fluid, suddenly unpin from the crust's imperfections, they transfer angular momentum in a violent rush. It's like uncorking a bottle of spinning liquid. The energy trapped below bursts upward, giving the star's surface a measurable kick. The strangest part, these events might be by the magnetar's crushing gravity, which warps the very concept of momentum preservation near its core. Another possibility involves cataclysmic fractures in the magnetar's crystalline crust. When these ultradense surface layers rupture, the star's moment of inertia shifts abruptly, much like an ice skater adjusting their arms mid-spin. But here's the twist. Magnetar crusts are theorized to be 10 billion times stronger than steel, meaning these quakes release energy equivalent to hundreds of millions of atomic bombs. The resulting recoil could literally torque the star faster, leaving astronomers scrambling to reconcile the numbers with classical physics. The most tantalizing glitch of all came from SGR 1935 plus 21.5, a magnetar that sped up by 1 part in a million, a tiny shift with massive implications. Analysis revealed its spin-up coincided with an X-ray flare, suggesting magnetic reconnection events might somehow inject energy directly into the star's rotation. This challenges the long-held assumption that magnetic fields merely break neutron stars. Instead, they might occasionally rev them like cosmic engines. Why does this matter beyond celestial curiosity? Because every glitch encodes data about conditions we can't replicate: matter at nuclear density, quantum fluids at macroscopic scales, and gravity's interplay with quantum mechanics. Some models even suggest glitches could reveal cracks in its relativity, hinting at physics beyond our current theories. When a magnetar hiccups, it's not just a stellar anomaly. It's the universe whispering secrets about the fabric of reality itself. Among the most intriguing possibilities about magnetars is that advanced civilizations might not just study them, they could harness them. Picture an interstellar highway system where these cosmic powerhouses serve as natural lighthouses, their predictable pulses cutting through the galactic noise like a beacon in the void. With spin rates so precise they rival atomic clocks and magnetic fields strong enough to warp spacetime, magnetars offer features that would make any spacefaring species take notice. The idea isn't as far-fetched as it sounds. After all, humans have used stars for navigation since ancient times. Why wouldn't a more advanced civilization engineer something far more sophisticated? Consider the practical advantages. A magnetar's X-ray pulses create unmistakable signatures, detectable across thousands of light years even in crowded. Unlike pulsars, which gradually slow down, some magnetars maintain their timing with extraordinary stability over decades, perfect for synchronizing clocks or marking transit points in a galactic network. Their immense energy output could also serve as a power source for hypothetical megastructures, tapping into magnetic reconnection events like cosmic hydroelectric dams. The sheer scale of energy available during a single flare could sustain an advanced society if they've mastered the technology to capture and store it. The most compelling evidence might already exist in the data. Astronomers have cataloged rare, ultra-precise bursts from certain magnetars that don't quite fit natural models. Some pulses arrive with suspiciously clean harmonic patterns, while others exhibit minute but deliberate variations, like Morse code embedded in starlight. Of course, the scientific consensus remains that these anomalies stem from poorly understood astrophysics, not extraterrestrial engineering. But the sheer potential has inspired serious academic papers exploring how an advanced civilization might modify a magnetar's emissions intentionally. One provocative study even calculated the energy requirements to artificially induce as signaling devices, concluding it's theoretically possible for a Type II civilization. Skeptics rightly point out the astronomical hurdles. The radiation environment near a magnetar would vaporize any known material, making direct engineering implausible with current physics. Yet alternative theories suggest remote manipulation, using precisely aimed particle beams or gravitational lenses to tweak the magnetar's emissions from a safe distance. Others propose that advanced beings might not need physical infrastructure at all, instead using quantum entanglement or spacetime manipulation to extract energy or information. While purely speculative, these ideas highlight how magnetars stretch not just the limits of physics, but of imagination. The deeper question isn't whether aliens are using magnetars, it's why we wouldn't look for signs that they might. As humanity's own technology advances, the line between natural and artificial phenomena blurs. Our radio telescopes, laser arrays, and even planetary radar systems now leak detectable signatures into space. If other civilizations exist, their equivalent of airport beacons or power grids might be hiding in plain sight, disguised as magnetar glitches or fast radio bursts. Every unusual pulse from these cosmic power plants could carry layers of meaning, some natural, some perhaps not. Until we know for sure, magnetars remain the universe's most tantalizing maybes. Imagine two magnetars locked in a deadly cosmic dance, each spinning faster than a kitchen blender, wrapped in magnetic fields strong enough to distort atoms from light years away, now orbiting each other so closely their gravitational pull distorts the fabric of space itself. Such a binary system isn't just theoretical. It would be the ultimate laboratory for testing physics under conditions so extreme they border on the impossible. The gravitational waves rippling from their orbit would carry distortions 1,000 times stronger than those from ordinary neutron star pairs, vibrating the very structure of spacetime with each close pass. Why would this be revolutionary? Because general relativity has never been pushed to its limits quite like this. When two ultradense objects spiral toward collision, their gravitational waves follow predictable patterns, but throw in magnetar-strength magnetic fields and the equations start to fray. These fields don't just bend light, they warp spacetime in ways relativity barely accounts for, potentially creating subtle deviations in the wave patterns. Detecting those anomalies could reveal whether theory holds up, or if we need new physics to explain how gravity and magnetism intertwine at the universe's most extreme scales. The hunt for these elusive pairs is already. Gravitational wave observatories like LIGO and Virgo are fine-tuned to catch the faint whispers of colliding neutron stars, but a binary magnetar system would scream across the detectors. Its waves wouldn't just ripple, they'd thunder, carrying distortions measurable even before the stars merge. Some models suggest their final death spiral could produce a unique magnetic echo in the gravitational wave signal, a fingerprint of field lines snapping and reconnecting as the stars tear each other apart. But the real prize lies in the collision's aftermath. When ordinary neutron stars collide, they create explosions that forge heavy elements like gold and platinum. A magnetar merger would be that on steroids, with magnetic fields channeling the explosion into jets of energy, so focused they could pierce through entire galaxies. The resulting fireball might even briefly outshine every star in the universe combined, visible halfway across the cosmos. And buried in that light could be clues about quark matter, dark matter, or other exotic states of matter we've only theorized. Yet for all their destructive potential, binary magnetars could also be cosmic lighthouses. Their combined magnetic fields might focus radio emissions into beams so intense they sweep across the universe like a searchlight flashing Earth with pulses of energy we could detect later. Some astronomers speculate that certain repeating fast radio bursts, those enigmatic cosmic signals, might actually be the death cries of distant magnetar pairs, their final orbits powering bursts detectable across billions of light years. The absence of confirmed binary magnetars so far is its own mystery. Given how many lone magnetars we've found, statistics suggest these pairs should exist. Are they vanishingly rare, or are we just missing them because their orbits dampen their telltale X-ray flares? Future telescopes like the Probe or the Square Kilometer Array might finally spot these duos hiding in plain sight. Until then, their potential remains one of astrophysics' most electrifying what-ifs, a chance to witness the universe testing its own laws under conditions we can't possibly recreate. Every unexplained gravitational wave signal, every odd radio pulse could be the first hint that somewhere out there, two magnetic monsters are circling each other, waiting to rewrite physics. When a magnetar meets its violent end, the universe might record its final moments in a language far more subtle than light, the faint ripples of gravitational waves warping the fabric of spacetime itself. Unlike the spectacular supernovae that birthed these cosmic monsters, their deaths could unfold with eerie silence in the electromagnetic spectrum, detectable only through the tremors they send reverberating across the cosmos. These gravitational wave signatures, what scientists poetically call a magnetar's death cry, would carry encrypted details about the star's last microseconds. From the moment its crust shatters to the instant its core collapses into something even stranger. The physics behind this cosmic farewell is as brutal as it is beautiful. As a dying magnetar's magnetic field decays, the unimaginable tension between its twisting field lines and the crushing force of gravity reaches a breaking point. The star's rigid crust, already under enough pressure to turn carbon into diamond 1 trillion times over, fractures in a final, catastrophic. This isn't just a crack, it's a total structural failure, sending vibrations through the neutron-rich ocean beneath at speeds approaching half the speed of light. The resulting oscillations warp spacetime itself, imprinting the star's death throes onto gravitational waves with frequencies too low for human ears, but perfect for detectors like LIGO and Virgo. What makes these signals so valuable is their uniqueness. When two neutron stars collide, their gravitational waves follow predictable spiraling patterns. But a dying magnetar's waveform would be unmistakable, a rapid crescendo of vibrations as the star's magnetic noose tightens, followed by abrupt silence if it collapses into a black hole, or a lingering hum if it transforms into an exotic quark star. Some models even suggest the magnetic field's collapse could twist spacetime in a way that adds a distinctive twang to the signal, like a plucked rubber band vibrating in an extra dimension. The hunt for these elusive death cries is already pushing detector technology to its limits. Unlike the milliseconds-long chirps of colliding black holes, a magnetar's gravitational wave farewell might last minutes or even hours, requiring observatories to sift through noise with unprecedented precision. There's also the challenge of distinguishing these signals from earthly vibrations, a task akin to identifying a single falling leaf in a hurricane using only a microphone. Yet the payoff would revolutionize astrophysics. Catching even one Magnetar's death cry could confirm whether these objects truly vanish into black holes or forge new states of matter in their final moments. Perhaps most tantalizing is the possibility that we've already recorded these signals without realizing it. Buried in LIGO's archival data might be faint, long-duration anomalies dismissed as glitches, each one a potential Magnetar's last whisper waiting to be decoded. Future upgrades to gravitational wave detectors, combined with AI pattern recognition, could turn these cosmic obituaries into routine observations, giving us front-row seats to the universe's most extreme physics experiments. Every ripple in spacetime becomes a time capsule, preserving the death of a magnetic titan in vibrations that outlast the stars themselves. At the edge of quantum physics and cosmic extremes lies a phenomenon so strange, it challenges our very definition of nothingness. Magnetars don't just bend the rules, they shred them, creating conditions where the empty vacuum of space itself becomes unstable. According to quantum theory, what we call empty space is actually a seething quantum foam, where particle-antiparticle pairs constantly blink in and out of existence too quickly to measure. But near a magnetar's surface, where magnetic fields approach a theoretical limit called the threshold, this quantum froth gets stretched beyond breaking point. The result: space itself begins spontaneously producing real particles from nothing, a cosmic magic trick where energy is pulled directly from the fabric of reality. This isn't just theoretical. The math suggests that when magnetic fields reach around 10 to the 15th Gauss, well within magnetar territory, the vacuum becomes polarized to such an extreme that virtual particles can no longer annihilate each other fast enough. Instead, they get ripped apart by the field's power, transforming from fleeting quantum fluctuations into measurable electrons and positrons. Picture a calm pond suddenly erupting with fish jumping out of nowhere. Except here, the pond is spacetime itself, and the fish are matter and antimatter appearing where only emptiness should exist. These newly minted particles don't just vanish. They get accelerated along the magnetar's field lines, creating cascades of radiation that could explain some of the most energetic bursts we observe. The implications rewrite what we know about matter creation. In laboratories, we smash particles together at nearly light speed to study fundamental physics. Magnetars achieve something far more profound. They pull matter directly from the quantum vacuum using pure magnetic force. This process might reveal exotic states of matter that can't form any other way, like a bizarre magnetic plasma, where particles align in crystalline patterns dictated by the field structure. Some theories even suggest that under these conditions, spacetime itself might develop a sort of graininess, evidence that at the smallest scales, the universe operates in discrete chunks rather than smooth continua. What makes this vacuum breakdown truly revolutionary is how it blurs the line between matter and energy. Near a magnetar's poles, where field lines are densest, the vacuum becomes a particle factory operating at nearly 100% efficiency. The energy required to sustain this comes directly from the star's magnetic reservoir, meaning every new electron-positron pair formed slightly weakens the field. This quantum drain could be why some magnetars fade into obscurity. Their incredible magnetic might slowly leaking away as spacetime itself siphons off their power to populate the universe with new matter. Astronomers might have already spotted the fingerprints of this process. Certain magnetar flares exhibit energy signatures that don't match any known atomic transition, but align perfectly with predictions of vacuum-driven particle creation. The most compelling evidence comes from bursts where the high-energy tail decays in a specific pattern, like watching someone turn off a faucet gradually rather than all at once. This matches simulations of how a magnetar's magnetic bottle would slowly exhaust its supply of freshly created particles after cracks open the containment. The deeper we look, the more magnetars reveal themselves as bridges between quantum mechanics and cosmic scale phenomena. Their ability to twist the vacuum into new forms suggests that empty space isn't so empty after all. It's a rich, dynamic medium that responds dramatically to extreme conditions. Future observations might catch these stars in the act of vacuum breakdown, giving us front row seats to one of nature's most spectacular displays. The moment when nothingness itself becomes something. The surface of a magnetar is anything but calm. Imagine a hurricane with winds of superheated plasma moving at relativistic speeds, all trapped in a magnetic vice so strong it bends the very atoms caught in its grip. These aren't just random bursts of energy. They're structured, chaotic storms raging across the star's crust, governed by forces we're only beginning to understand. Unlike Earth's weather, driven by temperature and pressure, magnetar storms are choreographed by magnetic fields so intense they could strip the electrons from your body at a distance greater than the moon's orbit. What fuels these plasma tempests? The answer lies in the magnetar's twisted magnetic field lines, which act like cosmic rubber bands stretched to their breaking point. When these lines snap and reconnect, a process called magnetic reconnection, they release enough energy to power 1 billion thunderstorms in an instant. The result is a cascade of charged particles, accelerated to near light speed, spiraling along the star's magnetic highways. Some get trapped in vortices, swirling like tornadoes of ionized gas, while others are ejected into space in jets, so focused they could drill through solid rock from light years away. But here, where it gets eerily familiar, these magnetar storms bear an uncanny resemblance to the solar flares and coronal mass ejections that erupt from our own sun, just amplified to apocalyptic levels. The same physics that governs solar weather, with its tangled magnetic loops and explosive releases of energy, plays out on a magnetar's surface with a ferocity that makes the sun's worst tantrums look like a gentle breeze. That similarity isn't just academic, it's a golden opportunity. By studying these hypercharged versions of space weather, scientists can refine models for predicting solar storms that threaten satellites, power grids, and even astronauts. Take the event of 1859, a solar storm so powerful it set telegraph stations on fire and painted the skies with auroras visible near the equator. If a similar event struck today, it could cripple global infrastructure for months. Yet compared to a typical magnetar flare, the event was a spark next to a supernova. The extreme conditions on magnetars let researchers stress test their theories in ways the sun never could, revealing hidden patterns in plasma behavior that could one day give us earlier warnings for earthbound solar storms. The most intriguing discoveries come from the way these plasma storms interact with the magnetar's solid surface. Unlike the sun's gaseous exterior, a magnetar's crust is a crystalline lattice of neutron-rich material harder than diamond. When plasma currents slam into this crust, they generate shock waves that reverberate through the star, creating seismic ripples detectable as X-ray pulsations. These are like cosmic tuning forks, letting astronomers map the storm's intensity and duration by reading the vibrations they leave behind. Some storms even leave scars, permanent rearrangements of the crust's magnetic footprint, visible in the star's subsequent emissions like battle wounds from a celestial war. Yet for all their violence, these storms might hold the key to unlocking one of physics' greatest mysteries: how matter behaves under conditions so extreme they defy laboratory replication. The plasma on a magnetar's surface isn't just hot. It's so densely packed and magnetically confined that it forms exotic states of matter, like bizarre liquid crystals or even quantum knots, where magnetic fields tie themselves into stable loops. Understanding these phases could revolutionize everything from fusion energy to quantum computing. proving once again that the universe's most destructive forces often double as its most ingenious teachers. Every flare, every ripple in a Magnetar's storm-racked atmosphere is a message in a bottle, cast across the void by nature's most unrelenting powerhouses. And as we learn to decode them, we're not just peering into the heart of a cosmic monster. We're uncovering secrets that could one day protect our own fragile corner of the universe. Magnetars aren't just confined to our Milky Way. These cosmic powerhouses have been spotted blazing across the vast gulfs of intergalactic space, their flares visible from millions of light-years away. When astronomers detected the first extragalactic magnetar in 2008, erupting from the nearby galaxy Messier 82, it shattered assumptions about how universal these magnetic monsters truly are. Unlike the predictable pulsars that fade into obscurity beyond our galactic neighborhood, magnetars announce their presence with violent brilliance, casting shadows across entire galaxies for brief, blinding moments. Their light becomes a cosmic stone, allowing us to compare how these extreme objects behave in different galactic environments, from metal-rich spirals to ancient dwarf galaxies, where the chemistry of star formation differs dramatically. The differences are already revealing unexpected truths. In the Large Cloud, a satellite galaxy of the Milky Way, magnetars seem to flare less frequently, but with greater intensity than their counterparts closer to home. One leading theory suggests this could trace back to variations in stellar composition. The Large Cloud has fewer heavy elements, meaning the stars that collapse into magnetars there might form with cleaner, more efficient magnetic dynamos at their cores. It's like comparing two lightning rods, one slightly rusted, the other pristine, and discovering the cleaner one conducts energy far more explosively. Even more intriguing are the magnetars found in starburst galaxies, regions where stars form at rates hundreds of times faster than in our quiet cosmic suburb. Here, magnetars appear younger and more volatile, their outbursts arriving in rapid succession like cosmic machine gun fire. Some astrophysicists speculate that the frenzied stellar nurseries in these galaxies produce magnetars with unusually thick crusts, trapping magnetic energy until it erupts in cascading. Others propose that frequent supernovae in these regions might leave behind clustered magnetars, groups of these magnetic monsters orbiting dangerously close, their interactions sparking chain reactions of flares. The ultimate prize would be spotting a magnetar in one of the universe's first galaxies, those formed less than 1 billion years after the Big Bang. Such a discovery could answer whether magnetars require specific chemical ingredients to form, or if they're a fundamental byproduct of stellar death across cosmic time. The James Space Telescope has already identified candidate neutron stars in distant galaxies by their telltale X-ray glows. Finding one with magnetar-level flares would be like unearthing a perfectly preserved fossil from the universe's infancy. What makes these intergalactic detections so challenging isn't just distance, it's timing. Unlike pulsars that broadcast steady beams, magnetars often lurk in darkness for decades between eruptions. Catching one mid-flare requires both luck and relentless monitoring. The most distant confirmed magnetar, located in a galaxy nearly 60 million light-years away, was only noticed because its gamma-ray burst happened to coincide with a routine scan by NASA's Swift satellite. Its light had been traveling since the age of dinosaurs, before serendipitously landing in our telescope's crosshairs. Yet every extragalactic magnetar we find rewrites the rules. Some appear to rotate slower than any in our galaxy, as if time itself stretches differently in their home environments. Others flare in energy ranges we've never observed locally, hinting at exotic physics triggered by their host galaxies' unique conditions. The grandest implication: magnetars might not be one class of object, but many, a family of stellar remnants shaped as much by their birthplaces as by the universal laws governing their collapse. As our telescopes peer deeper into the cosmic web, each new magnetic monster we uncover adds another piece to this puzzle, proving that even the universe's most extreme phenomena are far from monolithic. Deep in the cosmos, certain magnetars keep time with precision that would put Swiss watchmakers to shame, their X-ray pulses arriving with a regularity that rivals the most advanced atomic clocks on Earth. These aren't just cosmic oddities, they're nature's most accurate natural timekeepers, ticking away with such consistency that their rhythm can be predicted down to milliseconds across decades. Imagine a celestial metronome so reliable that its beats could theoretically guide interstellar voyages across thousands of light years, offering future spacecraft a universal reference point in the featureless void of deep space. The secret behind this astonishing precision lies in the magnetar's extreme stability. Unlike ordinary pulsars, which gradually slow as they bleed energy into space, some magnetars maintain their spin rates with minimal fluctuation. This is due to their incredible density. Imagine compressing the entire mass of the Sun into a sphere smaller than Manhattan, creating an object so rigid that even the most violent barely disturb its rotation. The result is a cosmic clockwork mechanism where the star's spin acts like a perfectly balanced flywheel, resisting changes that would throw lesser timepieces into chaos. What makes these magnetic timekeepers truly extraordinary is how their pulses cut through the noise of the universe. While GPS satellites rely on Earth-bound atomic clocks that require constant correction for relativistic effects, a magnetar's pulses come pre-calibrated by the laws of physics itself. Each X-ray flash is shaped by the star's gravity and magnetic field in ways that leave distinct fingerprints, allowing navigators to triangulate their position with astounding accuracy. Future missions could theoretically use these pulses like interstellar lighthouses, locking onto their rhythm to correct course during long journeys where even tiny drift could mean missing a target by billions of miles. The most tantalizing candidate for this role is SGR 1900+14, a magnetar whose pulses arrive every 5.76 seconds, with a variation smaller than 1 millisecond over 15 years of observation. That's comparable to an atomic clock losing or gaining less than a second every 3 million years, a level of precision that seems almost unnatural. Even more remarkably, its X-ray flashes contain harmonic overtones, subtle secondary pulses that could serve as built-in error correction, like the universe's own version of a checksum algorithm, ensuring the signal hasn't been distorted during its long journey. Practical applications aren't just science fiction. NASA's NICER experiment aboard the International Space Station has already tested using pulsar timing for navigation, achieving positioning accuracy within 5 kilometers in deep space. Scaling this up to magnetar-level precision could revolutionize how we explore the galaxy. Picture autonomous probes threading the needle between star systems by locking onto the steady heartbeat of these distant giants, their X-ray flashes acting as cosmic mile markers in three-dimensional space. Yet mysteries remain. Why do only certain magnetars exhibit this chronometer-like behavior while others spin erratically? Some theories point to crustal alignment, the idea that these stars must have magnetic poles perfectly aligned with their rotational axes to produce such clean signals. Others suggest it's a phase in their evolution, a brief window of stability before their magnetic fields begin decaying into chaos. Every new observation peels back another layer of this enigma, revealing how much we still have to learn about these celestial timekeepers. Beyond navigation, these precise pulsations offer another gift, the chance to test relativity under extreme conditions. As magnetar signals traverse warped spacetime near black holes or dense star clusters, their timing should shift in predictable ways if relativity holds. Any deviation from those predictions could hint at new physics, making these cosmic clocks both tools for exploration and laboratories for fundamental science. The universe has always provided guides for travelers, from ancient Polynesians steering by stars to sailors relying on magnetic compasses. As we stand on the brink of becoming an interstellar species, magnetars may offer the next great navigation aid, their unchanging rhythms cutting across the chaos of space like a conductor's baton keeping time for the cosmos itself. Among the four known fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, magnetars may be hiding clues to a fifth, something beyond our current understanding of physics. These cosmic powerhouses don't just bend the known laws, they stretch them to the breaking point, revealing anomalies that stubbornly resist conventional explanation. Take, for instance, the way certain magnetars experience sudden rotational speedups, glitches that can't be fully accounted for by gravitational or electromagnetic interactions alone. These irregularities suggest the presence of something else at play, an unseen influence acting on matter in ways its equations never predicted. One of the most compelling hints comes from the way magnetic energy behaves near a magnetar's surface. Even their monstrous magnetic fields, strong enough to distort atoms from thousands of miles away, shouldn't explain some of the bursts we've observed. The energy released during extreme flares sometimes exceeds what traditional models allow, as if an additional force is amplifying the output. Some theorists propose this could be evidence of a hidden interaction, one that operates only under the most extreme densities and magnetic intensities, making it invisible everywhere except in the hearts of these dying stars. The idea of a fifth force isn't entirely new. For decades, physicists have speculated about additional fundamental interactions that might operate over very short ranges or only under specific conditions. Dark matter, for example, could interact through its own undiscovered force, separate from the ones governing ordinary matter. Magnetars, with their unimaginable densities and magnetic fields, might be the only places where this force becomes noticeable, warping particle behavior in subtle but measurable ways. What makes this possibility so tantalizing is how it could reshape our understanding of the universe. If a fifth force does influence magnetars, it might also play a role in other extreme environments, black hole mergers, neutron-star collisions, or even the first moments after the Big Bang. The same hidden interaction could explain why certain subatomic particles behave unexpectedly in high-energy experiments, bridging gaps in quantum theory and cosmology. Of course, skepticism remains. Many observed anomalies might still be chalked up to incomplete models of known physics rather than a wholly new force. But with each new magnetar flare, each unexplained glitch in rotation, the case grows stronger that these objects are testing the boundaries of our knowledge. Future gravitational wave detectors and advanced X-ray observatories could provide the smoking gun, perhaps catching a magnetar in the act of breaking not just the rules, but the rulebook itself. Until then, magnetars stand as enigmatic laboratories, pushing the limits of known physics and daring us to imagine what else might be out there, hidden in the fabric of space itself. Whether they hold the key to a fifth force or simply expose the cracks in our current theories, one thing is certain: they're far from done surprising us. When a magnetar unleashes its fury in a burst of X-rays and gamma rays, the explosion doesn't just fade into the void, it lingers, bouncing off cosmic dust like a shout echoing through a canyon. These ghostly afterimages, known as light echoes, ripple outward for years, tracing paths through the otherwise invisible scaffolding of our galaxy. Each echo is a time-delayed whisper, carrying not just the signature of the original blast, but a map of every dust cloud and gas filament it encountered along the way. It's as if the universe handed us a flashlight and said, "Here, use this to see the unseen." The way these echoes form is a masterpiece of cosmic geometry. Imagine tossing a pebble into a pond. The ripples spread outward, hit obstacles, and create intricate interference patterns. Now replace the pebble with a magnetar flare powerful enough to outshine a million suns, and the pond with light years of interstellar dust. As the initial burst races outward at light speed, a fraction of its photons strike microscopic dust grains, scattering in all directions. Some of these deflected photons take detours, additional light years of travel, before finally reaching Earth, arriving months or even decades after the original explosion. The result, a series of expanding rings or arcs of X-rays that slowly drift across the sky, each one a snapshot of the burst's interaction with a different layer of galactic debris. What makes these echoes revolutionary is their ability to reveal the galaxy's hidden anatomy. By measuring the time delay between the initial burst and its echoes, astronomers can triangulate the precise locations of dust clouds that would otherwise be invisible. The echoes act like sonar pings, mapping the density, composition, and even the magnetic alignment of interstellar material with startling precision. One study of a magnetar flare in the constellation Sagittarius uncovered a previously unknown filament of gas, twisted into a helix by magnetic fields, a structure that had eluded detection until the burst's echoes illuminated it like a cosmic spotlight. But the real magic happens when echoes collide with one another. Just as overlapping ripples in a pond create complex interference patterns, intersecting light echoes can produce bright knots or strange, lens-like distortions. These anomalies aren't just pretty, they encode information about the dust's microscopic properties. Some echoes even polarize the scattered light, revealing how interstellar magnetic fields warp the paths of individual photons. It's like watching sunlight filter through a stained glass window, except the glass is light years wide, and the colors are X-rays carrying secrets about the universe's structure. The most famous example came from a magnetar in the constellation Cassiopeia, whose 2004 flare produced echoes that lingered for over a decade. As the light danced across nearby dust clouds, it revealed pockets of crystalline silicates, minerals forged in the atmospheres of ancient stars and blown into space by supernovae. These tiny cosmic gemstones, no larger than smoke particles, are the building blocks of planets, and their distribution hints at how our solar system's own ingredients might have been delivered. Yet for all their utility, light echoes also deepen the mystery of our galaxy's dust itself. Conventional models predict echoes should fade smoothly as they expand, but some magnetar bursts produce echoes that flicker unpredictably, as if passing through regions where dust clumps into bizarre, fractal shapes. Others show spectral shifts that suggest the dust's composition changes dramatically over relatively short distances, challenging assumptions about how evenly elements are distributed through space. Every echo is a reminder that the interstellar medium, far from being a uniform fog, is a dynamic, labyrinthine structure we're only beginning to navigate. The next time a magnetar erupts, its echoes won't just illuminate the present, they'll peel back layers of galactic history. Some of the dust these bursts reflect is older than the sun, remnants of stars that died before Earth formed. By reading their scattered light like pages in a cosmic archive, we're not just mapping space, we're reconstructing the life and death of the galaxy itself, one echo at a time. Deep within the heart of a magnetar's crushing gravity and swirling magnetic chaos lies a possibility so profound it could rewrite our understanding of reality itself: the temporary manipulation of the field. This invisible energy field, which permeates the universe and gives particles their mass, might behave in startlingly unexpected ways under the extreme conditions near these cosmic monsters. Picture the universe's most fundamental scaffolding, warped and stretched until the very rules of matter itself begin to bend. The field normally operates like an unseen ocean, with particles gaining mass as they swim through it. The heavier the particle, the stronger its interaction with the field. But near a magnetar, where magnetic fields approach 100 trillion times Earth's and gravity distorts spacetime into knots, this tranquil ocean might transform into a raging storm. Theoretical models suggest that the sheer energy density could locally excite the field, creating pockets where particle masses fluctuate unpredictably. An electron passing through such a region might suddenly weigh 1,000 times more, or momentarily become nearly massless, zipping through space like a photon. What makes this idea revolutionary isn't just the scale of distortion, it's the implications for particle physics. The boson, discovered in 2012 at CERN, confirmed the existence of this field, but we've only observed it in its calm, ground state. Magnetars could provide nature's own particle accelerator, exposing the field to stresses far beyond anything achievable in human-made colliders. Some theories even propose that under these extreme conditions, the field might briefly decay into a lower energy state, a catastrophic event dubbed a false vacuum collapse that could, in theory, rewrite the laws of physics in its wake. Detecting these effects would require almost unimaginable precision. One approach involves studying the light from Magnetar Flares for subtle anomalies in energy distribution, peculiar gaps or spikes that could indicate particles briefly changing mass as they escape the star's vicinity. Another method watches for unexpected patterns in gravitational waves emitted during, which might carry fingerprints of field disturbances rippling through spacetime. The most tantalizing possibility. Catching a magnetar in the act of emitting exotic particles that shouldn't exist under normal field conditions. Like a cosmic magician pulling rabbits from a hat we didn't know was there. The stakes couldn't be higher. If the field can be locally altered, it might hint at deeper layers of particle physics hiding beyond our current models. Perhaps mass isn't as immutable as we thought, or maybe the field itself has undiscovered interactions that only manifest under magnetar-level extremes. Some physicists speculate this could even open pathways to understanding dark matter, whose particles might interact with the field in ways visible only under such distorted conditions. Of course, skepticism remains. The energies required to significantly perturb the field border on the absurd, and some argue magnetars, for all their fury, still fall short. But history has shown that whenever we declare something impossible in astrophysics, the universe delights in proving us wrong. Whether these magnetic leviathans are quietly tweaking the cosmos's rulebook or not, their very existence pushes us to ask questions that straddle the line between established science and thrilling speculation. And in that uncertain space, where known physics frays at the edges, lies the potential for discoveries that could redefine everything we know about matter, energy, and the invisible field stitching reality together. 30th mystery, the Magnetar's legacy. Far in the future, when humanity has spread beyond our solar system and energy demands dwarf anything imaginable today, we might look to the corpses of magnetars as the ultimate power plants. These cosmic relics, long after their magnetic fury has faded, could become the crown jewels of interstellar industry, not just for their energy potential, but for the exotic matter locked within their ultra-dense cores. Imagine a civilization advanced enough to harness even a fraction of a magnetar's stored power. The energy from a single decaying magnetic field could sustain entire fleets of starships or power planet-sized megastructures we can barely conceive of today. The real prize lies in their composition. A typical magnetar's crust is a crystalline lattice of neutron-rich material harder than diamond, forged under pressures that turn ordinary matter into quantum curiosities. Some theories suggest their interiors might contain nuclear pasta exotic states of matter, where protons and neutrons arrange themselves into strands, sheets, and other bizarre configurations under the extreme gravitational squeeze. These materials, if harvested, could revolutionize everything from spacecraft shielding to energy storage. A thimbleful of magnetar crust material, if stabilized outside its native environment, might contain more usable energy than all the fossil fuels ever burned on Earth. But how would future engineers even approach such a monstrous task? The challenges are as daunting as they are thrilling. First, there's the distance. The nearest known magnetar lies over 10,000 light-years away. Then there's the environment. Even a dead magnetar emits lethal radiation and has a surface gravity 100 billion times stronger than Earth's. Any mining operation would need to contend with gravitational tides capable of shredding machinery, magnetic field remnants strong enough to scramble quantum electronics, and temperatures ranging from near absolute zero in the core to stellar hot plasma at the surface. The solutions might lie in technologies we're only beginning to imagine. Self-replicating nanomachines could be deployed to disassemble the star layer by layer, converting its material into usable forms while withstanding conditions no human-made structure could survive. Alternatively, colossal magnetic scoops might harvest the particle winds still streaming from its poles, capturing the star's slow energy bleed like a cosmic water wheel. Some speculative designs even propose using controlled to tap the magnetar like a cosmic oil well, releasing stored energy in manageable bursts rather than catastrophic flares. Beyond practical applications, magnetar remnants could serve as cosmic waypoints for galactic expansion. Their incredible density makes them ideal gravitational anchors for navigation. Imagine a network of these ultradense markers, their positions fixed against the stellar background, guiding ships through the interstellar void. The periodic pulses of those still rotating could function as universal timing signals across thousands of light years, synchronizing clocks for civilizations separated by vast distances. Yet the most profound legacy of magnetars might be what they teach us about the universe's resource limits. These stellar corpses represent matter pushed to its absolute extremes, showing us the upper boundaries of density, magnetism, and energy storage. In their slow decay over billions of years, they demonstrate how even the most violent cosmic events eventually become resources for whatever comes next. The same forces that once made them destroyers could make them the ultimate enablers of interstellar civilization, if we're bold enough to reach for them. Perhaps one day, among the stars, our descendants will speak of magnetars not as cosmic monsters, but as the lighthouses and power stations that lit their way across the galaxy, the remnants of nature's most violent physics experiments repurposed as engines of exploration. Their story would come full circle, from creators of cosmic chaos to cornerstones of cosmic community. Magnetars do more than defy physics. They redefine what it means to be awestruck. In a universe where black holes steal the spotlight, these magnetic monsters whisper a humbling truth. Reality's imagination outstrips our wildest fiction. Consider that the gold in your smartphone likely formed in a cataclysmic collision between neutron stars, a process so violent it briefly outshines entire galaxies. Yet magnetars take this cosmic alchemy further, their flares forging elements under conditions no lab could replicate. They're not just celestial oddities, they're mirrors reflecting humanity's insatiable curiosity back at us. This connection runs deeper than science, for humans have mapped constellations to navigate oceans and mark seasons. Today, we train telescopes on magnetars, decoding their pulses like celestial Morse code. The same wonder that guided Polynesian voyagers by starlight now drives astrophysicists to parse X-ray flickers from 15,000 light-years away. It's a continuum of exploration, from wooden ships to quantum sensors, all fueled by the question, what else is out there? Technology bridges these eras. The instruments tracking Magnetar Flares evolved from Galileo's first telescope, each breakthrough expanding our vision. When NASA's NICER experiment used neutron star pulses to test GPS-like navigation in space, it proved that studying these extremes isn't abstract, it's paving humanity's path to the stars. Even the algorithms analyzing Magnetar data owe their origins to code written for early space missions, a digital lineage stretching back to Apollo. But the true magic lies in Magnetar's ability to unite disparate minds. A farmer gazing at the night sky and a physicist crunching equations share the same spark of wonder when a Magnetar's gamma ray burst paints the cosmos with invisible light. These events remind us that the universe doesn't discriminate. Its mysteries await anyone daring to look up and ask why. Perhaps that's their greatest lesson. In a fractured world, Magnetars offer a rare constant, the certainty that beyond our atmosphere, physics plays by rules indifferent to human divisions. Their flares illuminate not just interstellar dust, but the shared hunger for discovery that makes us human. And as we stand on the threshold of becoming an interstellar species, these magnetic sentinels whisper that the next chapter of exploration will be written not just in equations, but in the collective awe of billions staring skyward, united by curiosity. From reshaping spacetime to seeding galaxies with gold, Magnetars stand as cosmic puzzles with profound implications, not just for astrophysics, but for humanity's understanding of reality itself. These celestial powerhouses force us to confront the boundaries of known physics, revealing phenomena so extreme they blur the line between science and speculation. Consider how their magnetic fields twist the vacuum of space into particle factories, or how they send vibrations through quantum matter we can't replicate on Earth. Each discovery peels back another layer of the universe's hidden rulebook, proving that nature's imagination dwarfs our boldest theories. Yet Magnetars offer more than scientific revelations. They redefine our cosmic perspective. Every gold atom in your jewelry, every unexplained burst of energy from deep space, even the subtle warping of spacetime we're only beginning to measure, ties back to these magnetic titans. They're not distant curiosities, they're active participants in shaping the universe we inhabit. The same forces that could sterilize a planet from light years away also forged the heavy elements necessary for life, embodying the universe's dual nature as both destroyer and creator. As technology advances, so does our ability to decode their secrets. Next-generation telescopes will catch Magnetar flares in unprecedented detail, while gravitational wave detectors listen for the spacetime ripples from their collisions. Quantum computers may soon simulate their interiors, offering glimpses into matter's behavior at nuclear densities. Each tool brings us closer to answering existential questions. What happens to matter under infinite pressure? Can magnetic fields truly warp the fabric of reality? Are we seeing hints of physics beyond theories? But the most thrilling possibility is what we haven't yet imagined. History shows that every time we push the boundaries of observation, whether discovering pulsars or confirming gravitational waves, we uncover phenomena that rewrite textbooks. Magnetars, with their ability to turn empty space into a particle generator and time into a malleable fluid, likely hold surprises that will make today's boldest theories seem quaint. The next great breakthrough in physics might not come from a lab, but from the flickering X-rays of a dying star 20,000 light-years away. If you've ever stared at the night sky and wondered what secrets it holds, Magnetars are your answer. They remind us that the universe is stranger, more violent, and more magnificent than we could ever conceive. So keep looking up, because somewhere out there, a magnetic monster is bending the rules of reality, and with each observation, we're learning to speak its language. Don't forget to share which Magnetar mystery fascinates you most in the comments, and join us next time as we continue exploring the cosmos's greatest enigmas. Until then, stay curious. The universe has only begun to reveal its wonders.